Alright. Damped harmonic motion. Our first extension of simple harmonic motion. We will have forced harmonic motion before we're all done with this. So let's kind of sketch out a situation. We've got our mass on a spring, set up to run horizontally again. But we're going to make a little bit of a change. We're going to take this whole thing and stick it underneath a fluid that has a damping coefficient to it. Now, back in chapter 6 of the Pasadena book and I think it's chapter 5 of the Mount Sac book, there's a discussion about damping forces. And there are two different types, one that's proportional to the velocity and one that's proportional to the velocity squared. This particular type is the proportional one that we're working on. If you've got the proportional to velocity squared one, it would be a different result. It would actually be a nonlinear differential equation, which would be a bit harder to solve. If we think about the forces that would be acting on this, we'd still have things like the normal and gravitational, which aren't very interesting to us. And then we'd have forces like the minus kx, and possibly as it begins to move in the other direction, a minus bv. Now, the minus sign is there to indicate that it's opposite the direction of the velocity. So if it's getting pulled back in the negative direction, the force is in the positive. If the block is currently getting pushed in the positive direction, the force would be in the negative direction. If we write the sum of forces equals ma, we're going to have a minus kx minus bv equals ma. A quick rearrangement later to put everything on the same side and isolate the acceleration. And we'll get this. Notice that's a different linear differential equation. If I write in the components of it, we've got the second derivative of position with respect to time times b over m with the first derivative of position with respect to time. Oops, not with respect to space, but time. And then k over m with respect to where you are. This has a different result. And if I have the time, I will be recording a short video that talks a little bit about how it's solved. But again, this is something you don't need to know for this class, you just need to know what this results in. So, what do we end up with? Well, there are actually three possible outcomes for this. So this equation has three possible outcomes. And it's essentially going to come from, we assume a solution that has something like e to the omega t, and we'll get, once we plug it in and do some cancellation, omega squared plus b over m times omega plus k over m equals 0, which you'll notice that that is, in terms of omega, a quadratic equation, which means the possible omegas are going to look like minus b over m plus minus the square root of b over m, the whole thing squared, minus 4 times k over m all over 2. And I'll rearrange that quickly for a moment. There is a point to me going through this, even though I'm not going to show you the full solution. Can take the 2 inside, and we get something like this. The main thing you notice is there are possible solutions depending on what happens inside the square root. So one possibility, and it's not a super interesting one to us at the moment, is that b over 2m minus k over m is greater than 0. This turns into a case that gets called overdamped. So in overdamping, it doesn't actually oscillate. If we watched x as a function of time, we pull it to the side, we let it go, and it relaxes back towards its initial position 0, basically relaxes back to the spring being unstretched and uncompressed over some long period of time. If we keep messing around with this, there's another case. If b over 2m minus squared, my bad, minus k over m is equal to 0. This gets called critically damped. It's actually pretty similar to overdamped in that you start out somewhere and you relax back towards 0. It just does it in a more reasonable amount of time. And the last outcome is really why we're here. It's the damped harmonic outcome. If b over 2m squared minus k over m is less than 0, that means the inside of the square root is imaginary, and if we have imaginary exponentials, those are sines and cosines, then that ends up being underdamped. And in an underdamped case, you'd actually have oscillation that dies away over time. And we have a solution for that. X would look like some amplitude, your release point, times e to the minus b over 2m. And I want to point this out. The b over 2m was there. Since we assumed the form of an exponential, that's actually going to exist no matter what we do. We'll have a damping term. And then we'd have a cosine of omega t plus the phase. However, omega is a bit more complex here. It's going to be the square root of k over m minus b over 2m squared. Or more generally, in case you happen to deal with a pendulum case, you can also think of this as just omega naught, the natural frequency with no damping. Oops. Alright, I'm also cutting off things a little bit, so let me move that up. Omega squared minus b over 2m squared. Okay. Or you might have this. Okay. So you can get several different possible things happening here. Each one of them is interesting in its own way. Usually things like the suspension on cars will be something like critically damped-ish, or fairly close to it. You don't want it to oscillate a lot. You want it to hit a pothole and kind of bounce maybe a little bit, but pretty much relax back to where you were. Talking with students in the past, one of them suggested that overdamped may in fact be what you want if you have a piece of artillery. Your cannon goes off and it shoots the projectile. Well, you don't want it to relax back as fast as possible. You want it to do it a bit more sedately than that. Underdamped, well, of course, you know, if we want a mass in a spring that damps away slowly, that's what we want. Where do you actually tend to see underdamped type cases? Well, it actually happens in electronics a lot. If you've got a little bit of resistance in a circuit, normally you don't want the resistance in the circuit. What you want is the oscillating behavior. So unfortunately you can't entirely get rid of the damping part. So unless you're doing a forced oscillation case, you're just going to have damping over time. Alright. So that's information about damped harmonic motion. Like I say, if I have time, I'll record a little bit more about solving the differential equation for those of you who have that as an interest. I'm not going to promise that this chapter. I am going to try and get one for the simple harmonic case, but I don't know that I'm going to get to the one for damped harmonic in time. But there we go. Damped harmonic motion. 3 outcomes: overdamped, critically damped, or what we're interested in this chapter, underdamped, where it oscillates but dies away. Okay.